All right, here at the end of this chapter, let's go through an AP titration free response example. Okay. Aniline, a weak base, reacts with water according to the reaction represented above, where aniline plus water produces C6H5NH3+ and hydroxide ion. Part A, write the equilibrium expression Kb for the reaction represented above. Kb is the concentration of the products C6H5NH3+ times the concentration of hydroxide over the concentration of the reactants C6H5NH2. Part B, a sample of aniline is dissolved in water to produce 25 milliliters of a 0.1 molar solution. The pH of that solution is 8.82. Calculate the equilibrium constant Kb for the reaction. Okay, the first thing we can do is, knowing the pH, we can calculate the pOH. And we want to do that because our Kb expression includes hydroxide ion. Given the pOH, we can find the concentration of hydroxide ion. 10 to the minus pOH is a concentration of 6.61 times 10 to the minus 6. This is also the concentration of the other product, C6H5NH3+. Now we can find Kb. We can substitute the concentration of the products, or 6.61 times 10 to the minus 6 squared, divided by the initial concentration of the aniline, 0.10 molar. And we get a Kb of 4.4 times 10 to the minus 10th. Part C. The solution in Part B is titrated with 0.1 molar HCl. So you have a weak base being titrated with a strong acid. Calculate the pH of the solution when 5 milliliters of the acid has been added. So the first thing I do is use my given concentrations and my given volumes to find the number of moles of aniline and HCl. So 0.025 liters of aniline times 0.1 molar aniline is 0.0025 moles of aniline. 0.005 liters of HCl times 0.1 molar HCl is 0.0005 moles of HCl, or H+. Okay, and I'm showing here the neutralization of the aniline. Okay, so we start with our initial amounts. We're going to go ahead and use up all of the H+ and have some excess aniline. And in doing so, we generate some of this conjugate acid here, 0.00050 moles. Now we need to find the concentrations because we have a buffer situation here. I'm going to make a little correction here and I'll make it right on the slide. This is neutralization. So this is before neutralization, when neutralization occurs, and after neutralization. That should be correct on your slide. But what we're talking about here is the neutralization of the aniline with the acid. Okay, so now we need to find our concentration of our base using this amount and our concentration of our conjugate acid using this amount. Okay, so we have 0.0667 molar aniline and 0.0167 molar conjugate acid. Okay. Now we still have to find the pH. What's going to happen here is we have a buffered solution now, right? So the pH, we can use Henderson Hasselbach to find the pH. So that's what we'll do here. So I showed using the ICE table, although I rarely use the ICE table now that I do Henderson Hasselbach. You can follow that alternate solution if you want to. I'm going to use Henderson Hasselbach, which I wrote using the POH. So POH is the pKb plus the log of the acid over the base concentration, or the minus log of the Kb, which you calculated in part B, 4.37 times 10 to the minus 10, plus the log of the acid, 0.0167, over the base, 0.0667 concentrations, which again, we just got done calculating in part C. So we get a POH of 8.76, and that would give us a pH of 5.24. It does make sense, by the way. We should probably check our work. We are titrating a weak base with a strong acid. So we should get a pH that is slightly less than 7. All right, let's go back to part D. Part D says calculate the pH at the equivalence point of the titration of part C. So when we did part C, maybe you noticed we were before the equivalence point. So let's find the pH at the equivalence point. Okay, so at the equivalence point, the moles of C6H5NH2 have to equal the moles of H+. And we already calculated in a previous slide our starting moles. We did this in part C of aniline. And so when the number of moles of H+ equals that, that's how we know that we're at our equivalence point. Keeping in mind that we're going to be also creating or producing this conjugate acid in equal amounts. Okay, so 25 milliliters of HCl is needed to reach the equivalence point. And how do we find that out? Just remember that MA VA equals MB VB. So just remember the concentration of both the acid and the base was 0.1 molar. We started with a volume of the aniline, 25 milliliters, which means we need a volume of acid also equal to 25 milliliters. That brings the total volume of the solution to 50 milliliters. So now I can figure out what's going on at equilibrium. And to say, so I have some moles of C6H5NH3+, and in 0.050 liters or 50 milliliters is a concentration of 0.050. And I have, remember this will undergo hydrolysis to produce this base aniline and excess hydrogen ion. So we decrease that by amount of X, increase the other two by that same amount X, and we can solve. So here's the thing. We know Kb. We calculated Kb in part B. But we need Ka here because this is the conjugate acid. So Ka is 1 times 10 to the minus 14 over the Kb, 4.4 times 10 to the minus 10, which is 2.3 times 10 to the minus 5. And so, again, assuming that that minus x is really small, we can say that the Ka, 2.3 times 10 to the minus 5, is equal to the concentration of the products, x times x, over the concentration of the reactant, 0.05. Solve for x. X in this case happens to be the hydrogen ion concentration, 1.1 times 10 to the minus 3 molar. The negative log of that gives us a pH of 2.96. Last but not least, the pKa values for several indicators are given below. Which indicator is most suitable for the titration? Justify your answer. So in general, we want a pKa value close to the pH at equilibrium, or at the equivalence point. The pH at the equivalence point was 2.96. So we want to pick an indicator that has a pKa value near that equivalence point. And so that would be the erythrocene. And so to justify our answer, we can just say the pH at the equivalence point is acidic. The best indicator then is erythrocene, for which the value of the pKa is closest to the pH at the equivalence point.